Let's do a quick recap on discrete random variable. Okay, I'm going to use the same example as I have used with you guys since the beginning of this year, and it's also going to be the same example as what I have on the Achevas TV, which is let's say we have a box, and within the box I have different numbered balls. So I have 10 balls that is inside this box. Let's say I have I have 3 of the balls with number 4 on it. I have, let's say, 2 of the balls with number 6. And maybe let's have 5 balls with number 9. So 1, 2, 3, 4, 5. 5 balls with number 9. And our aim now is to try to find the average number that is contained within the box. How do we find the average number that is contained within the box? Average. The average number that is contained within the box, if I were to just try to do a calculation, it is going to be 4 plus 4 plus 4. There are 3 4s here. Then plus 6 because there are 2 6s. And plus 9 plus 9 plus 9 plus 9 plus 9. There are 5 9s. And because there are 10 objects here, because there are 10 balls inside here, so I'm going to divide this by 10. And if I remember correctly, this should be 69 over 10. This is the average. It is something that we have been calculating. I think no matter how our school tried to define the idea of average to us, ultimately, right, because we started off so far back, in Sec 1 and Sec 2. So after we have done this calculation multiple times, we start to feel, through calculations, through the numerical calculation, we start to feel the what exactly is this average. So it became our daily speech, like the average temperature in this month is this, the average marks in the class is this. We don't even think about it that much. And I want to make sure that I possess this idea of average all the way until I try to discuss about this discrete random variable, because in the last 5 years, this word average has changed. Then after a while, do you realize when you were in your Sec 3 and Sec 4 in your E-Math, they started to change the word. They replace this word average in your math textbook from average. Let me write it down here, okay, so that we can still know that we are talking about exactly the same thing. From the word average, they start to introduce to you another word. This becomes a bit more mathematical. You don't use this word as much, okay, but it is the word mean that they replace it with, the word mean. In a Sec 1 and Sec 2, for example, if there were to be just 10 balls that is inside the box, yeah, this is actually a pretty good way for you to calculate average. But what if there are 100 balls that is inside this box? If there were to be 100 balls that is inside this box, trying to do a calculation this way may not be the most efficient. So as they try to introduce to you mean, they also introduce to you another way to organize the data. They introduce this table. The table which is of X versus F, the frequency. They introduce the frequency table. So if you were to look at the information that is given, we are seeing that there are 4, which happens 3 times. There are 6s inside, which happens 2 times. There are 9 inside, which happens 5 times. So instead of doing a calculation like this, which you have to do it 10 times, just extrapolating this to 100 times, it is going to be very, very difficult, for you to just press everything into the calculator. So by reorganizing the data first before we try to do a calculation, we can then rewrite this as 9 times of 5. This was when we start to try to reorganize statistics into a table form. The moment when we have a larger sample size, we are going to start to experience repetition. But we know that there is some problem with this also when it comes to statistics that is probably even bigger. For example, going from 100 balls to 1 million balls that is inside here. From 100 balls to 1 million balls that is inside here, which is something closer to what we are doing now. Okay, we are doing statistics where the sample size can grow pretty large. And that is when we are thrown another term again. So on top of mean, on top of average, expectation, we are now looking at mean, or we are now looking at average as the expectation. Expectation is average, expectation is mean. The way that we are going to view information is going to be changed again. If you were to look at it from another perspective, what kind of perspective? Let me show you what kind of perspective, okay? It is like 9 happens 5 times, right? It is useful information. Like 10,000 people carry 4 handphones, right? It is useful information, but we can make it even more useful by changing the way that we are going to be processing our expectation. So we can rewrite this again as 4 times of 3 over 10 plus 6 times of doing a manipulation to this 2 over 10 plus 9 times of 5 over 10, which in the end, I'm still going to be calculating the same number. It is the mean, it is the average. But what is the difference? The difference is by reorganizing the data yet one more time, I'm now introduced to another table. This other table is called the probability distribution table, because I know what is 3 over 10, 2 over 10, and 5 over 10. 3 over 10 is the probability, which means that now we know another piece of information because we just reorganize the information that is given. We know that this is going to be happening 3 out of 10 times, 5 out of 10 times. So by reorganizing my information so that I focus on 9 and this, you know what is this? This is not 9 happening 5 times. This is 9 happening half the time. 5 over 10 is half. 9 happening half the time. It is like me now not trying to tell you just one piece of information, one perspective, which is the number of handphones, number of people carrying 4 handphones every time when they go out of the house, right, is 10,000. Now I'm telling you that it is 10% of the population. Can you see the difference? Knowing that it is 10% of the population gives me the possibility of setting a policy for the whole Singapore. When I talk about very, very big data that is like this, I think something that is relative to the population size is always more useful. So we are now adopting this perspective instead. So if I were to look at it from this perspective, this 69 over 10 can also be calculated by generalizing this into summation of x, which is x here, multiplied by the probability that x is equal to x. Okay, and this can also explain to us why, if I were to be doing, for example, expectation of a particular function. If I were to try to find the expectation of a particular function, it is going to be the sum of that particular function, for example, f(x), multiplied by the probability that x is equal to x. For example, if I were to try to find the expectation of x squared, okay, from x, I let it go through a function, which is to square it. What is the probability of, what is the expectation of x squared? What is expectation? To start off with, expectation is the average. So the expectation of x squared is like having this same table, but working with x squared. So we have an x squared, we have a 4 squared, we have a 6 squared, we have a 9 squared. I'm just trying to look at all the individual numbers that is inside this box and I square them. So what is the probability of getting a 4 squared? What is the frequency of getting 4 squared? The frequency remains at 3. The probability will remain at 3 over 10, which means that to calculate this, it is still going to be equal to 4 squared multiplied by 3, since it happens 3 times, 6 squared multiplied by 2, then after that 9 squared multiplied by 5, because the frequency didn't change, which also implies that the probability will not change. So this is going to be this, multiplied by 3 over 10, multiplied by 5 over 10, which gives me a summation of x squared multiplied by the probability that x is equal to x. X going through some kind of function will not change the frequency, and it will also mean that it will not change the probability that it happens. Variance, let me write it down, okay? Variance. What are we trying to capture for variance? We are trying to capture the spread of the data, correct? Variance is actually an average. It is the average of x minus away mu square. In this particular case here, x is equal to, expectation of x is 69 over 10. So in this particular case here, this mu is 69 over 10. It is a constant. If you were to be using this, right, then you're going to be doing summation of x minus mu, which is 69 over 10 square, then multiply by probability of x is equal to x. You've got to go through this same process. The other version is very, very easy also. It is just the expanded version of this. What do I mean by expanded version of this? Expanding this as an algebra, it is going to be x minus 2 mu x plus mu square. And we know all our expectation stuff. Expectation of this plus this plus this plus this is the same as, x squared. Expectation of x squared minus away, 2 is a constant, mu is a constant, mu is like 69 over 10 here. So 2 mu, I can sort of like take it out of the expectation notation, so it will be just expectation of x plus mu square is a constant, so expectation of a constant is the constant. So we have this. So this is going to be equal to expectation of x squared minus, what is expectation of x? Expectation of x is mu. So if expectation of x is mu, we have mu times mu, which is going to be equal to minus 2 mu square plus mu square. This is going to be equal to expectation of x square minus away mu square, or if I want to change this notation, I can try to write it as this form, expectation of x, which is mu, the whole thing square.